Hello, everyone. Welcome. Thank you for being here. For those who don't know me, my name is Max Odkins with the Fire and Resource Assessment Program here at CAL FIRE, and I'm very excited to welcome you to this invited presentation in our Forest Health Research webinar series. We're joined today by Dr. Malcolm North from the U.S. Forest Service Pacific Southwest Research Station and the University of California, Davis. For this presentation, what is forest resilience and how do we measure it? Today's presentation is part of our Forest Health Research Program, which is funded in part by California Climate Investments, which is putting cap and invest dollars to work in communities throughout California. This program aims to prioritize and fund research in forest health and fire science critical to the state of California, share scientific information, and support statewide plans, including the California Wildfire and Forest Resilience Action Plan. We typically have solicitations for research grants on an annual basis, and so far we have funded 114 competitive grants through this program for about $34 million. You can find out more about that program at the link that's posted on this slide or at the QR code that's also posted on this slide. You can also use that webpage to sign up for updates about upcoming grant solicitations in the future. Before we get started, just some brief housekeeping. We will be recording this presentation and it will be posted alongside recordings of our past webinars on the website that's listed on this slide. You can also sign up for notifications specifically about upcoming webinars if that's of interest to you as well. We'll have a Q&A session at the end of this presentation, so please go ahead and type your questions into the chat at any point during the presentation, or you can use the raise hand feature and we'll allow you to unmute and ask your questions during the Q&A at the end of the presentation. With that, it's my pleasure to introduce Dr. Malcolm North, who is a research forest ecologist at the U.S. Forest Service Pacific Southwest Research Station and an affiliate professor of forest ecology in the Department of Plant Sciences at the University of California, Davis. His research includes work on examining forest restoration and ecosystem response, wildfire, and forest carbon dynamics. His lab primarily focuses on forest and fire ecology of the Western U.S. And the conifer forests therein. Thank you so much for being here with us, Malcolm. Please take it away.
All right, thank you very much, Max. And as a note, Max was one of the people who survived being in my lab and lived to tell about it. So it's been great to see him really thrive in CAL FIRE. But I appreciate the invitation, Max. Thanks. Let's see if I can get my screen going here. Okay, you see that?
Yes, looks good.
All right, thank you. So what I want to talk about today is this concept of forest resilience and how we measure it, or how I think we can measure it. And in the process of doing that, I'm going to be talking about some of the ways that I think we're beginning to understand how these frequent fire forest systems are put together. And to my mind, some of the fairly significant implications of what that means in terms of how we're currently managing them and whether that's in sync or out of sync with what some of these research studies are telling us about how these forests operate. But with that as a bit of a teaser and an introduction, I do want to acknowledge and say particularly I'm very grateful to my co-authors of this paper that came out back in 2022 in Forest Ecology and Management. The co-authors included the late Ryan Tompkins, who's sorely missed, Alexa Bernal, Brandon Collins, Scott Stevens, and Rob York. So I'm going to start with fairly basic context setting that I think it's going to raise some interesting questions for us. So first we have to look at, Western conifers have always been thriving in these systems that are actually pretty stressful systems. At least the dry Western forests, frequent fire forests, for centuries have exposed those forests to extreme droughts and fire in the past. So why are many of the trees nowadays dying? And of course, the obvious answer is, well, the fire patterns are much more extreme these days, particularly the advent of extensive crown fires and the high severity effects that come with those. Um, but we're also seeing, of course, a lot of drought mortality and significant mortality in the Sierras that a lot of studies have suggested have to do with competition associated with stand density. Obviously, you keep fire out of the system for a while and you continue to get more and more trees. And I love trees, but trees are basically gigantic drinking straws. And you've got too many straws in soil that often has a very limited water holding capacity. And that eventually leads to stress for the trees. And often the final coup de grace or mortality is caused by bark beetles themselves, who are very good at sensing that stress, that water stress. So one last kind of context slide here, and I want to talk a little bit about the interaction of modern fires, which have really changed fundamentally in how they burn, and the drought mortality that is stoking those fires, and particularly stoking the amount of fuel loads that we have. There's a really nice paper done by Scott Stevens, also back in 2022, in which he looked at the Creek Fire and what it was telling us about the conditions of that fire. So preceding it, of course, you had a 4 to 5 year drought in which, by various estimates, you had 120 to 150 million trees die in the Sierras. But unlike kind of the steady fuel loading you get from branches breaking off and litter coming down, in these cases, you have much heavier, large fuel loads coming into the system, particularly the boles of the trees, in this case, often 25, 30 inches in diameter, a really sizable amount of piece of wood and fuel that can really drive intense fire behavior. And so in the middle panel, you can see the pyrocumulus nimbus cloud that was created on September 6th, which was probably the peak running day of that fire. And I am not a physicist, but I have a friend who is, and I was just curious. I said, you know, what kind of energy release does it take to be able to loft smoke and particulate matter to 55,000 feet, which, as I understand, was at the time and may still be a record for the amount of the height of smoke coming off of the fire. And he was ballparking that it may have been basically at the energy release of a small atomic bomb. And that's a pretty substantial amount of both fire danger and threats that can come from a system that's burning at that level. And this paper that Scott was working on had a very interesting summary of the conditions in that fire, which you can see in this right-hand panel of the thermal image of the fire on September 6th, again, the peak day. The interesting thing about this is usually in wildfires, the heat is on the perimeter because the fire is expanding into new areas and burning, and that's the running direction of the fire. But in this case, you can see that most of the heat release is actually happening on the interior of the fire, most likely because of that massive amount of large woody debris that was a result of the 2012 to 16 drought. And one of the co-authors on this paper is Mark Finney, who I think is probably one of the best fuels people we have in the country in terms of looking at fuel dynamics. And he basically proposed in this paper that the kind of fire behavior that we're seeing is well outside of any of the current models we have for predicting fire intensity. In fact, made this comment that the only real analogs you have for this kind of fire are mass fire events such as Tokyo and Dresden in World War II from saturation bombing campaigns. That's a pretty, to me, a fairly frightening idea, because the last thing you want to do is put people out on the front line of one of these fires with that level of energy release going on. In fact, in a fire where we have very little ability to predict how it's going to respond and where it's going to go. So with that said, I'm going to shift gears a little bit and talk about resilience, and believe me, it will circle back to these questions that I've raised. But I think that one of the first places to start is, what the hell is resilience and its baggage? And I will tell you, I was one of the last people who I thought would ever write a paper about resilience, because it's this concept that kind of drives me nuts. It's kind of like trying to nail Jello to the wall. It's it just means all sorts of different things to different people. But to start with, I think when I first started working in California in the 90s, the kind of default goal for forest management was to try to restore some semblance of pre-European conditions. And often you'd have discussions about, well, if you're in mixed conifer, we'd be trying to shoot for at least 8 trees per acre that were 30 inches or more in diameter. Very structurally focused restoration goals that was going on. But once we moved into the 21st century, the degree of climate change that was going on, as well as the fundamental change in the fire regimes in the West, really made those ideas of kind of going back in time impossible and not very practical. And at about that time, in 2012, the Forest Service Planning Rule came out and explicitly emphasized resilience as a goal for managing forests. The California Task Force went the same way. And of course, I don't need to keep on going, but most of the talk these days in terms of trying to build ecosystems that can deal with these stresses is to be able to have some level of resilience in the system, so that we're not simply winding the clock back in time, but we're trying to make a system that can absorb or at least be able to resist and possibly respond to these different disturbances in climate conditions, which do not have a historical analog. But because of that, resilience has actually been pretty difficult to define. And maybe it's just a bunch of academics quibbling over it. But frankly, I've seen surveys suggesting that forest managers are often just as confused by what the hell resilience is as researchers are, because there's confusion over the types of resilience. For instance, there's a difference of resilience in the engineering world from what it is in the ecological world. There's a question of what scale you apply it at. Is it the individual tree, the ecosystem, the landscape? The terminology actually gets confused. What is recovery versus resistance versus resilience? And then, of course, you're going to have resilience itself be variable between different ecosystems themselves. So this article Branton Jacks had an analysis of resilience in which they mentioned that it was a malleable term that facilitated communication but did not have very well defined targets. And that's certainly what my belief was when I came into looking at this question of what the hell resilience is in frequent fire forests. Some of the researchers involved have said that you can't really talk about resilience unless you're willing to define resilience of what, to what, and what is the appropriate spatial and temporal scales. So for this particular section of the analogy of resilience, I'm going to talk about assessing resilience as the ability of frequent fire forests, i.e. those that used to have low intensity fires burning generally less than every 35 years, those forests to be able to retain their inherent structure, composition, and functional integrity in response to stresses that are common to the forest type, such as fire, drought, and insects, at the ecosystem to landscape level over the age span of the dominant trees, 300 to 400 years. That takes a very nebulous type of subject and really tacks it, hopefully, to the wall by being very specific about the ecosystem that we're looking at and how we're going to judge it. So I'm going to take a bit of a different approach here, in that how I first got into this idea of even thinking about resilience was a kind of confluence of 3 different things that really had struck me. And first is ecological concepts. And don't worry, I'm not going to get into a whole bunch of theories, but I am going to talk about the way ecology views fire in forest systems. And secondly, what the literature has to say about the development of increasing stand density and its effect on trees and forest systems. And then third, and hopefully most concretely, take a fairly rich and extensive historical data set and analyze it in part using a civicultural metric, which I'll provide some background on here in a minute. So those are going to be the three-pronged approach to dealing with trying to define resilience in this system. And from that, we'll go to some ideas about what might be going on in the system. So the first, ecological concepts. In forests that have fire in them, the ecological analog is that it's very similar to herbivory in grasslands. You have consumption as a top-down limitation on the ecosystem's biomass, which means that if you do not have a limited supply of grazers, as in the bottom picture, zebras and bison, and if they proliferate, they end up limiting the growth of the plants so that the plants rarely get big enough to compete with each other for resources. So what does this mean in terms of forests? Well, generally before fire suppression, we have lots of very extensive tree ring records that low intensity fire was frequent in these systems, often anywhere from 5 to 25 years recurrent interval. And that kind of fire was limiting the density of the trees. And by inference of that, if it's limiting the density of the trees, it's probably keeping the trees from having to compete for resources such as water, light, and nutrients. So I'm going to suggest that frequent fire forests may have well evolved with little or no competition. And that's what I'm going to be talking about, particularly when we get to the historical data set, is trying to document that. But I first throw out this teaser. I'm always very interested in the way the Sierra Nevada forests were described by some of the earliest people coming to see them, and particularly by surveys that were done. And probably a bunch of people on this call know that Liebert was one of the people who did extensive timber surveys in the Sierra Nevadas. And he had this very interesting quote that I ran across when I was reading some of his old summaries of forest conditions. He considered the forest understocked, and he said, "The suppression of the young growth has always been one of the serious results of fire. The land does not carry more than 35% of the quantity of timber it is capable of supporting." So I want you to think about that. And this 35% number is going to come up again as something significant and kind of surprises me as to how well Liebert managed to nail this. But keep this quote in mind as we go forward on this, because I think it has some interesting ramifications. So the second prong approach I was going to take a look at is historical summaries, or excuse me, literature summaries of what is generally decided by the research community is interacting factors, kind of the ecophysiology of what's going on with trees when you have fire suppression active in them. And certainly, again, these forests used to survive fire and drought, but something is fundamentally different now in these systems. So if we look at what the drivers of these might be, we can at least build the general assumptions about what's probably going on in the forest. Obviously, without the fire, the live tree density and biomass goes up. The competition for growth resources certainly gets pretty intense, as you can tell from a picture like that in the upper right-hand corner. Tree vigor is likely to decrease, in fact, will decrease. And with that, you have an increase in drought susceptibility. There are quite a number of papers that generally agree on this consensus for what one of the major effects are of fire suppression in these systems. But this Caloret paper is certainly a very good one. I just put as an example because it's got such an incredibly large data set, over 5,000 trees sampled on, I think, 120 different sites, finding this kind of level of pattern of competition increasing the increasing competition for growth resources, and tree vigor decreasing and drought susceptibility going up. So with that, I'm going to suggest something here about why we might be seeing so much mortality currently in these forests forests that survived centuries of drought exposure and fire continuously. One of the things that we know about these systems is that when trees grow rapidly and have high vigor, they're actually quite good at defending themselves against stresses such as fire, drought, and bark beetles. And the picture on the right shows a common response of trees to bark beetle attacks, in which they produce a lot of sap, which ends up entombing the beetles and basically killing the beetle in its little larval tube that it's excavated. It's a very water intensive process to be able to produce that level of pitch, but it is something that's a common tree defense, particularly when the trees have abundant levels of water in them. The thing I'm going to suggest here is that what you've probably got going on is inter-tree competition is fundamentally different than a short-lived fire or drought event, because it creates a chronic growth reduction and increases tree susceptibility to stress and mortality, following roughly this kind of water going down the drain illustration that Jerry Franklin had in this old article about tree death as a process. But it's an interesting concept because what they propose, and as far as I know is still commonly supported by a lot of data, is that as you get stress in trees from competition, they end in a downward spiral in which the tree rings get shorter and shorter, the vigor of the tree ends up being reduced. And fairly recently, a researcher in Sequoia, Adrian Das, pointed out that you can actually pretty well predict which trees are going to die in these stands once they cross a reduction in radial growth that goes past a certain threshold. It's very unlikely the tree is going to recover from that stress. So the hypothesis in this case that I'm going to present is that in the past, frequent fire forests were resistant to stress pulses, fire, drought, pests, beetles, because those stresses were fairly short-lived, such as anywhere from a 1 year to a 3 or 4 year period. But that these frequent fire forest systems may not be adapted to novel stress presses, the kind of continual stress that happens with a competition that does not go away. So if resilience is about restoring minimal competition, how do we measure it? This is one thing where I think we're actually in a fortunate condition, is that civiculture has for a long time had a measure of competitive levels in forest stands, and the metric is a stand density index, or SDI. And it's a fairly simple measure that is just combining the number of trees per acre and their size measured with diameter to assess how much total forest biomass there is, or often it's expressed as basal area. As you can see in this lower part of this slide, where you have 4 different stand densities, both in metric levels of basal area and below it in English units. Civiculturalists have taken this measure one level further, in which they use the stand density index, or SDI, and make it relative for each stand condition against the maximum that a particular forest type can support. So in this case, if you look at the right-hand side, you've got a local stand that you're trying to assess how competitively stressed it is, of ponderosa pine, and it's got an SDI of, let's say, 140. From sampling a whole bunch of stands that are out there, you can develop this kind of upper threshold determination of what a maximum amount is that a ponderosa pine stand can support. And in this case, the lower slide roughly gives you a representation of what that might look like, an SDI of 400. So the measure being relative is fairly simple. It's just taking the 140 dividing by the 400, and that gives you a relative SDI of 35%. And civiculturalists have used this for a long time and generally categorized levels of competition in stands at 4 different levels. Between 0 and 25%, it's considered a stand as relatively free of competition. At 25 to 35%, it's in a state of partial competition. And in 35 to 60%, you're in full competition. And then you're in the one greater than 60%, the one I like, the zone of imminent mortality, which is basically where the trees are going to start dying because their biomass is exceeding the demand of the resources, particularly water in the system. Okay, so with that as a background, we're going to dive into this historical data and apply this relative SDI to assessing how conditions have changed. And fortunately, both Brandon and Scott Stevens had worked with data sets and published papers back in 2015, a pretty extensive data that was developed back in 1911 in both of these forests. In fact, the sample size was so high that they basically sampled 5 to 10% of the total number of trees, which I think is something on the order of 25 or 30,000 trees across these plots that were systematically put in the forest. And that's what these boxes are in the upper right-hand side. What we did was we took that data and split it into forest types because we're interested in applying this relative SDI, and that depends what the maximum level is, depends on what type of forest type you're looking at. So in this case, we had 3 different pine mixed conifer, xeric mixed conifer, and mesic mixed conifer forests that the data divided itself into. But before I dump into the next slide, I think there's a picture here which was taken roughly in that area that I have circled up there. And it really shows this transition going on in these forests between a historical clump of pretty large pines in the center of the photo, surrounded by a lot of ingrowth or small tree infilling, which has come in with the suppression of fire. So what does this mean in terms of forest conditions? Bear with me on this. You don't need to get into all the guts of the numbers here. I'm going to cover it in a minute, but you pretty much get the entire story looking at the comparison of the Bear Creek Ranger Station on the right-hand side, what it looked like in 1911 and then in 2005. But to walk you through a little bit of this, because this really tells the heart of the story, the top row with the colored histograms is what the conditions were like in 1911. And the bottom row is what the same plots, the same areas were like in 2011. And in the historical data set, we actually know what all the species are, so we can look at the color levels to determine the different species abundance. The bottom one is using a combination of techniques, an F3 program that does not allow us to actually divide it into species, but it does give us size and density. And so if you look at what's going on here, the first thing to point out is that the range level, the y-axis, is an order of magnitude larger in the lower row of plots than it is in the top, 80 versus 8. But I think the thing to mainly look at is in the upper right corner of each one of these graphs, I put in what the density was, the number of stems per acre, and the average size, average diameter of stands in each one of these 3 forest types in 1911 and in 2011. And you can see that the density on average has increased by 6 times what it was in 1911, and the average tree diameter has dropped 50%. And when I first published this paper, I got a response from some environmental groups that said, oh my God, here's somebody who's trying to justify the, going back to getting the cutout. I just want to point out in this bottom right-hand side that this this discussion about what is stressing the forest is not thinning the forest as a pseudonym for or an excuse to make a timber grab, because what we're really looking at is trying to reduce the number of stems in these systems and the level of competition, and that almost all of those stems, 75% of those stems, are in, at least the stands we were looking at, less than 15 inches, most of the time less than 12 inches. So you are not getting any timber out of these stands by trying to retreat them, by trying to treat them and reduce the density level in them. So let's take a look at this in terms of the shift in the competitive environment. And this is where this relative stand density index is going to come in. And what you've got here is the 3 different forest types in these boxes: pine mixed conifer, xeric, and mesic mixed conifer. And then these graphs are on the left, they're paired in each one of these. And on the left-hand side is the conditions in 1911 versus 2011. And the plot or the number of points indicate the abundance of stands at that particular level. And you'll notice that across these graphs, there's a dash red line, a larger dash red line, and so on. These are dividing this area of relative SDI into what it equates to. So below 25%, the bottom is considered free of competition, partial competition 25 to 35, full competition, and then that dreaded zone of imminent mortality at the top. So what can we make from this? These are called violin plots for obvious reasons. But if you look at the historical data sets, which is the left-hand pair in all of these plots, you'll see that in 1911, 73 to 85% of the stands were free of competition or in partial competition at most. If we look at the current condition, the 2011 in the black circles, contemporary forests, 82 to 95% of those stands are in full competition or in the zone of imminent mortality. I just look at these figures and I go, the violins have basically flipped between the historical condition and the contemporary condition. And to me, it's a very strong indication that the competitive environment and the stress level in these forests has fundamentally changed from what it used to be like and was like for eons with a frequent fire system compared to a system in which we've kept the fire out of it. So historically, resilient forests were low density with little competition. And you might go, yeah, so what? We kind of knew that, you know. There's a lot of trees out there. There's obviously a lot of competition for water and resources. You know, we've known this. What difference does it make? Well, I think that, at least for me, when you start thinking about a forest that evolved in a system with very little competition to manage forests where we focus on manipulating levels of competition to produce desired stand conditions, it fundamentally suggests that we're often managing these forests and treating them in a kind of condition which these forests did not evolve with. And so on the right-hand side here is a stand density management diagram. I'm not going to go into all the particulars of this, but this is basically the kind of engine or the man behind the curtain in FVS, the Forest Vegetation Simulator, which is widely used by the Forest Service, as well as many private companies will use it. And it shows that you can pretty much try to plan what a stand that you're managing will be like from a certain number of trees that you plant, the initial density, when you would thin those stands, and as you thin them and reduce the density, how you'll get increases in diameter, which eventually on this diagram suggests that at 20 inches you harvest the stand because you've reached your target diameter. But all of the way the stand is managed and the way it's planned from beginning to end and what is going on in these FVS simulations is all trade-offs in the level of competition as expressed between the number of stems in the stand and the size of those stems. Forestry practices often maintain stocking above 35% of maximum to sustain tree growth and schedule thinnings, and try to thin the stand as it approaches 60% to capture the density dependent mortality. So you're not just leaving the trees to die out there in the woods, particularly if they're large enough, you may be able to get a commercial thin out of them and be able to reduce the density of the stand. What does this suggest, though, about how we're managing forests and we're thinking about this? I would suggest, first off, is that relative stand density index of 35% should be a maximum rather than a minimum. That is fundamentally below the level at which almost all managed stands are kept at in terms of the number of stems out there and the biomass that they're carrying. And to give you an example, we took the current standard in the Forest Service in California, in which they consider priority stands for treatment as those that have a relative SDI of equal to or greater than 60%. And so if you applied that particular metric to the stands that we sampled in and that we analyzed for the 2011 period of the data, you would only treat 48, 25, and 0% of the contemporary pine, xeric, and mesic mixed conifer plots that we were measuring. If you flip this definition and said, however, treatments to minimize competition would be much higher than that, and you try to keep the stand at or below 35% relative SDI, those levels of the percentage of stands you need to treat increase to 96, 91, and 100% of the 3 forest types. So it unfortunately is kind of sad news for the level of management and the dire condition of the type of stands that we're in, but it does suggest exactly how much bigger the process or the problem becomes when you get into looking at these stands as having a potential relative SDI of 35% or less. One thing that I find interesting about these relative SDI numbers is that it does give you a fair amount of flexibility to create different forest conditions, but I'm going to argue that it's not a license for even spacing, which is the reaction you would get from many people when they say, okay, well, if trees are having problems with competing with each other, let's try to separate them as much as possible by planting them on an evenly spaced grid. But if you look at the historical range of the relative SDI values, they were between 14 and 39%, suggesting that you actually can manage forests and have some of those forests be in denser, higher biomass conditions where there's a lot of soil moisture. These would be the type of stands where you might well be able to support spotted owl habitat or higher levels of canopy cover. But you've also got other areas that are going to be on more xeric, drier conditions where open forests are going to be more the norm, and which are probably going to look at something in that 15 to 20 or 25% relative SDI value to try to maintain a more open condition that the limited water supply can actually maintain. I think one of the things that, and I'm harping on this point a little bit, but I think that there's a real tendency in the way we manage forests to try to space trees as evenly as possible to delay their competition going on. But there's been a lot of work done recently suggesting the spatial pattern in these forests is very important in terms of their resistance to wildfire, and particularly this ICO pattern, or individual trees, clumps of trees and openings, makes for much more resilient forest conditions than regularly spacing trees within a stand. Very important paper just came out today suggesting that this high level of homogeneity and high level of tree density that is particularly found on private industrial lands could be causing some of the problems of extreme wildfire and much higher levels of high severity fire than you would find on stands that had more of this ICO and open pattern. So in sum, I'm going to say that fuels reduction is much needed, and it's a priority system that we need to keep on top of because it is the fundamental driver that's often destabilizing the most impactful disturbance in the system, which is fire. But we should never forget that it's fundamentally triage. It is not solving the fundamental problem of what is stressing the forest and keeping it susceptible to other things like drought and bark beetles. With changing climate and disturbance regimes, forests need to be resilient to a variety of stresses in addition to fire, and that resilience is going to require very low tree densities that significantly reduce competition and try to keep competition low in these stands. It's really fundamentally the only way we'll probably be able to maintain some of the ecosystem services that we really prize in these forests, such as carbon storage, wildlife habitat, particularly for wildlife associated with large trees, and pest and pathogen resistance will also depend on having more vigorous tree growth that is not being diminished by competition for resources, particularly for water. Thank you, and I can take any questions at this point.
Great. Thank you so much for this presentation, Malcolm. It's really nice to have you here with us presenting this research and this synthesis. It's such an important topic and one that I know has gotten a decent amount of attention in the state recently. This idea of relative stand density index and what the targets should be. It's fantastic to have you here presenting in depth about it. So just wanted to have everyone join me in thanking you for the presentation before we switch over to Q&A.
Thank you, my pleasure.
All right, so with that, we are about to switch over to the Q&A. I'm going to stop the recording, and this is a reminder that folks can please put your questions in the chat or use the raise hand feature, and we'll get to your questions, as many of them as we have time for here. So go ahead and start thinking about your questions. I'll end the recording and we'll switch over to Q&A.